wabarakatuh. My name is Indra bin Suha. My number is 221-091-117. So today I would like to present my FYP. Okay, this is a table of content. Okay, so for introduction, my project title is Design a Circuit Breaker Transient Coupling Voltage Response for 35 kV overhead line for lightning protection and pressure conservation. Objective for my project is analyze the behavior in 35 kV lines under lightning-induced fault and also to investigate mitigation strategy. So the main tool that I use is PSCAD. Okay, so why is PSCAD? PSCAD is industry standard software for power system. It also has highly accurate in simulating complex engine event, and also easily to integrate with power system design and analysis system. So there is a few feature and cost of integration. At the entire screen, it shows the circuit diagram before fault, and it divided by three parts, which is sources, transmission line, and also load. Okay, so this is the control panel, which is this function is to control the value of frequency and also the voltage. Okay, so I will show how to make the graph. Put channel like this, then connect it like this, and also rename it like this. Also this. And then right click. Okay. Okay, so I will run this simulation. So as we can see at the graph, it shows that there is the current flow before the breaker. After 0.1 second, the overcurrent triggered the circuit breaker. After second 0.2, the current flow became normal. For E1, which is a voltage before circuit breaker, it shows the continuous voltage of flow where the peak-to-peak graph value is 35 kilovolt. And for E2, which is the voltage after circuit breaker, it shows the same trend with breaker current. And for the last one, it shows the TRV, where there is some voltage occur after the breaker is triggered. Therefore, I put fault at this circuit like this. And also adding one more thing to measure, which is IA. When I will run it, okay, so it is the graph for E1, E2, line current, TRV, and also breaker current. I put surge resistor in the circuit. Then we run it. Okay, so as you can see, for E1, the voltage fluctuation are much smaller compared to the previous graph without the surge resistor. And then for E2, the light E1, the voltage have also stabilized with less extreme oscillation. For TRV, the TRV show much smaller oscillation. With the surge resistor in place, the TRV is more controlled. And for the breaker current still show some oscillation, but the spike are reduced. And for the last one, the line current is similar to the breaker current. The line current is more stable. It means that the surge resistor reduce the intensity of the current and also leading to the less fluctuation in the current flow through the line. It has a few limitations, which is first one is accuracy with high frequency transient. Next is complex model, and next is computational power, and also it have environmental factor, and also it have fault modeling, which is limited in simulating complex real-world fault scenario like flashover and multi-phase fault. And for the last one, it integration with other tools. So for the conclusion, these tools support PSCAD and EMTDC enable accurate simulation of TRV and lightning-induced fault in a 35 kV overhead transmission line. It also allowed evaluation of mitigation strategy like surge resistor, control switching, and grounding improvement. The strength for this software is high accuracy in simulating power system and TRV behavior, and also user-friendly interface for modeling complex fault scenario, and also widely used for trusted in the industry. And the constraint for this simulation is struggle with simulating high frequency transition and fast event, and also simplify complex components such as arrestor and circuit breaker. And the last one, it requires significant computational resource for large computation.